Welcome to exam number 3 review for ECE 320A, and hopefully you can guide me on what you want to see or not see as we're going through. But let me just indicate what I'm thinking you need to be ready for on Thursday, which is in a few days, relative to topics. And there's really sort of 3 main themes, but the long list you can find on D2L. The main themes are you need to be able to perform or work with S-domain circuits. You need to be able to play with transfer functions inside and out. And when I say play, we're actually getting into the fun part of the semester. Now we have a lot of tools that we can actually play with or use. And the other main topical theme is convolution. Relative to these 3 topics, the exam will be dealing with 3 homework problem sets, and the 8th problem set is due tomorrow. That's problem set number 8, and hopefully that's clear. It is maybe talking about some topics that we haven't explicitly defined in class, but I hope you can figure that out when it starts talking about cutoff frequency or break frequency. In those, it's a first order circuit, and there's really only one frequency that you need to worry about, is what I'm hoping. But if you have questions, please let me know. If you're looking for practice problems, you can actually look back. I don't know if you remember or not, but last time on practice exam number 2, I kept crossing out some and saying you're not really responsible for those questions or problems. Now you are. Now for exam number 2, some problems that you can go back and look at would be problems 2, 5, 6, 7, and 10. Those deal with S-domain circuits, writing the equations. And they deal with initial value theorem, final value theorem, and I think that's roughly the concepts that those questions address. Then on practice exam number 3, we haven't yet made it to some of those questions, but most of the problems you can be responsible for, and I would say those are problems 1, 3, 5, 6, 7, 8, 9, 10, 13, 14, and 15. Those, I think, are valid problems. Exam 3, the practice exam, was dealing with the fact that the students at that point knew how to sketch Bode plots. We may start on that tomorrow, but that directly won't be on there, but I think that information will be helpful in your understanding of what's going on when you're analyzing circuits. So I haven't yet decided whether we will begin that new material tomorrow, but it will help you for exam number 3. Those are some problems that you can look at. In terms of expanding on these 3 topics a little bit more, well, do you have any specific questions right now dealing with those 3? A lot of people said, oh, this is too early to have our review. I haven't started studying. So now you're probably listening, trying to understand what it is that I'm wanting you to be ready for, and you may not be armed with questions. In terms of the first topic, which is transformed circuits, if I give you a circuit, whether that has independent sources, dependent sources, op-amps, etc., you better be able to take it from the time domain into the S-domain. That's what I'm hoping. So you need to be well-versed in transform circuits or transform circuits into the S-domain. And with that in mind, you need to be able to deal with all of the possible types of solutions, and in particular, you need to be able to handle the initial conditions that can arise from inductors and capacitors. That's what I'm wanting you to be able to do. I also want you to be able to, for my sanity, put it into a matrix. If I say, here's the vector of unknowns that I want you to be dealing with or working with, can you put that into a matrix form? Where the main matrix might be an impedance matrix. If you were writing a lot of mesh equations, you now have these impedances times the currents, meaning if I give you something that looks like this is dangerous when I'm making something up on the fly, but you should be able to put that into a matrix form. If I say write this in terms of mesh currents, what would you, and I might say that there are particular initial conditions involved with the energy storage devices. How would you then translate these initial conditions, or how many initial conditions would you have? You would have 3 initial conditions, and you also have the source V1. You don't know whether that's going to be non-zero before t equals 0 or not, and I would have to tell you. But now if you were translating that into the S domain, you would want to put a source there, a source there, and a source there, and put all of these in terms of their S domain impedance values. And as long as I haven't indicated anything in the time domain, I could say, okay, this is now V sub 1 of S, the Laplace transform there. Now I need to know how to inject those particular initial conditions. And you should be able to either put those in as voltage sources or current sources, depending on whether you're doing mesh type analysis or nodal type analysis. Here I'm suggesting that you want to preserve the mesh structure, and so now these would be initial conditions where this is now L, I sub L of 0 minus. If this was, let's say, the I sub L direction, and likewise then, if this was the I sub L sub 2 direction before, then I would have this minus plus, and this would be L sub 2. So I should say this is L sub 1, this is L sub 2, I sub L of 0 minus. And the capacitor would now have this plus minus V sub C of 0 minus over S. And if you now wanted to write this, maybe you call this I1, this is I2, and this is I sub 3. You should now be able to write this in terms of those initial conditions as sources, and those currents, those are your unknown variables, I sub 1, I sub 2, and I sub 3. And on the right-hand side, you will be eventually having sources, meaning I'm looking to find or I would be wanting to see something like this. Here are your sources, and here are your impedances. And this you could say is the Z11, the Z12, the Z13. This is Z22, Z32, meaning the first subscript is the row subscript, and these are all there. You have potential 9 elements in the impedance matrix, and now you have the different sources, and you would have then 3 rows of sources. If we looked at the first row, in the diagonal term, I would be adding up all of these impedances that I1 touches. And that would then include R sub 1, R sub 3, and the L1 impedance and the C impedance. Meaning the Z sub 1, 1, since I know I would be running out of room, was R1 and R3. It was the L1 impedance, and meaning now I'm simply looking at what happens when I write KVL around that yellow highlight. And I now have the 1 over SC, and that's the Z11 term that I would expect you to have. In terms of the source, if I say something, let me call this maybe S1 as far as the row entry, what does that look like? And now you're looking at whether these sources enhance or hinder your flow of the current I sub 1 that you've drawn as positive. Meaning I would introduce the V1 with a positive sign, since if you increased V1, that's going to make the I1 larger. Does that make sense? Then the initial condition associated with the inductor, how does that come in? That's also positive. And this particular initial condition term would come in with a minus sign, because if you increased it, it would impede I1, or it would essentially be trying to make reducing I1 in the positive sense. Meaning S1 now becomes this expression, V1 of S, whatever that happened to be, plus the initial condition due to the first inductor, that's L sub 1, I sub L sub 1 of 0 minus, and then minus the initial condition due to the capacitor. And that would be, all of that is the term in that first row of the source column. And you just continue to fill that in. Question?
I forget how we know which way to put those initial conditions.
So now the question was, how do we know how to put the initial condition sources in? What I would suggest that you do, it's in a table, I think, in the book, and make that a part of your crib sheet, essentially. But all of that comes from the current voltage relationship of the inductor and capacitor. Meaning, if you remember, and this is what I told you to know until you retire, for the inductor, that's Eli, that says that V sub L is L di sub L of t dt. Now if you simply Laplace transform that, or take it in from the time domain to the S domain, you have V sub L of S is now L times the Laplace transform of a derivative, which is S I sub L of S minus I sub L of 0 minus. And now this shows you that the voltage across that inductor in the S domain really is made up of 2 pieces. One piece due to the impedance of the inductor, and the other piece due to the initial condition. And that's how you really justify the relationship of those. In this case, it's the voltage source, meaning now from this, hopefully it's clear that if you needed to move this into the S domain, you have this impedance, that's right there, but now this piece needs to come and be represented as a source. And that now says, oh, if this complete drop across those two is V sub L of S, and this is the direction that I had originally indicated for my positive current flow through the inductor, now if I do a KVL essentially around here, I can see that V sub L of S is actually SL times I sub L minus plus L I sub L of 0 minus. And that's where the voltage source comes from the inductor. And you should be able to now solve this expression here for I sub L of S, meaning now I sub L of S is equal, if I divide every term by SL, I have 1 over SL V sub L of S. And if I put this initial condition term on the other side, I have a plus, and I've divided by SL, so I now have I sub L of 0 minus over S. And correct me if I'm wrong, but this is now the nodal form of that inductor's relationship that you would use. And I like to actually be very explicit with this and say, oh, I have my inductor current really consisting of two parts. Here's the first part, and here is my impedance, where this is the total drop across that inductor. And now this initial condition says, oh, I also have a current due to the initial condition, and I'll represent that, or a part of my total inductor current is not only due to the impedance SL term, but also the initial condition term. And that's how I like to sort of insert my inductor in the S domain if I wanted to perform KCL type equations or right node equations. I would replace that inductor with this kind of a structure. Does that answer your question? And you can do exactly the same analysis for the capacitor. It will just be dual in nature. That's then the first piece, which is putting all of that. And like I said, now you're ready to really play, because now you can take any circuit and put it in the S domain. And once you're in the S domain, you have all sorts of transfer functions and inputs or sources that you can play with. If you now are going to, let's say, the second topic, which is transfer functions, now you can really, this is where I get excited in terms of manipulating things or playing with systems. You now, once you have a transfer function, I hope it's very clear that you have poles and zeros available to you. And when the book starts talking, and this is maybe going a little bit beyond what we need now, but it may start talking about breaks. And if you have a pole or a zero, it's going to break at some point, unless it's a pole or zero at the origin, and then it never breaks. It's always on. But if you have a linear polar zero or a complex polar zero, they will have breaks associated with them. And the way that I like to think of those breaks is, if you're dealing with a zero, after the break, your magnitude plot is going to go up. And why? Well, one way to sort of mnemonically remember that is that's associated with the zero, and the zero is concerned with the numerator, and the numerator is on top of your transfer function. So that kind of reminds you, oh, I'm going up if I run into a zero at a given frequency. Likewise, if you now run into a pole factor, your magnitude plot is going to break down after that break frequency, and that's because the poles, are associated with the denominator terms, and the denominator's in the basement or down. But once you have a transfer function, you can identify these poles and zeros, and once you have poles and zeros, you can do all sorts of things. You should be able to very quickly determine the structure of the response. And I hope by this point in the semester you know what I mean by structure of the response. And the structure of the response actually allows you to very quickly determine whether or not that system is stable. And just looking at the pole zero, so I could give you a pole zero diagram and say, answer the following questions. And here are my, in the black color, I sort of have questions that you now should be able to answer. You should be able to find the sinusoidal steady state. Now you may need to have a little bit more information than just poles and zeros. You may need the gain information, which is not explicitly present in the S-domain picture of poles and zeros. But you need the sinusoidal steady state from, let's say, an input, x of t, that might be a cosine omega naught t. You also should be able to apply the final value theorem. But when can you do that? What do you need to look for if somebody gives you poles and zeros? What are you looking for in order to apply the final value theorem? Pardon? You need to have your poles all in the LHP, the left half plane. And you could also do the initial value theorem. And something that will, well, maybe this is getting a little bit ahead of the game, but you now could start to think about the shape of your frequency response, because you now know where the poles and the zeros are. Or you can walk along the imaginary axis and see what the height is above you, the circus tent, and that's actually your magnitude response. And for the next class, well, even for this one, from the S-domain poles and zeros, you should have a pretty good indication of how long the transient will last. If you shake this system and now you quit shaking it, how much longer after you stop shaking it will you continue to see something at the output? And that's based on where your poles are located, because the poles influence your transient behavior or the natural response of your system. And the other thing that maybe this is a little bit beyond where we've gone, but if you needed to simulate this in MATLAB, which is your next course, but I've also shown you a little bit of that in the homework solutions, how fast do you actually have to sample the waveform? How fine do you need to resolve? Meaning, if I give you, so here's what I'm referring to. If I gave you something like this, and let's say this is -2, and let's say this is J5. I don't know why I'm picking odd numbers, but I am. What would you expect to see if that was the pole zero diagram for a given h of s? If I now said, what's h of t? Structurally, could you tell me? That's the main parts, isn't it? Your real part is the decay, and your imaginary part is how fast it moves up and down, or the damped frequency. And now whether or not you include and say, well, I don't know what A is unless you give me more information, and I don't know the angle, let's say, but that's now the structure of your response. This would now look something like, in the time domain, that. And this envelope is governed by e to the minus 2t, and this frequency is this is associated with the damped frequency, which was 5, and that's 2 pi f sub d, which is 2 pi over t. And now if you needed to plot this in MATLAB, you might say, well, I want to really see this picture or what's happening, and so you may say, I want to put 30 samples, and I'm not putting 30 samples in every cycle of that oscillation. And then if what you're saying is I want to divide capital T by 30, and that's now my sampling period. This is more than you came to find out, but that's what I'm saying. If you needed to sample that or picture that, and you might exaggerate this, and you may say, well, I want better resolution than that, so I want 50, and somebody else might say, well, I want better than that, I want 100. That's really up to you, how fine you want to split that up. But that's what you're doing, and you want to capture that oscillation. Questions on that? So if I gave you the following picture, and I said, there's your system, and that's the pole zero diagram, could you immediately write down the structure of your impulse response? Everybody understand what I'm asking? Is that making sense? If I give you that picture and I don't give you anything else, would you feel comfortable visualizing or at least writing down the structure of your impulse response? If I said this is the pole zero diagram of a system's transfer function h of s, and what are you looking for or looking at? For the structure, what's important? What can you sort of neglect in that picture? The zero. The zero just influences your weighting on the various terms, how you combine the different pieces. How many pieces are you going to have in your impulse response? And now you could say it depends, right? Somebody could say 2 and somebody could say 3, and those answers could be correct depending on how you interpret your impulse response. If you say, I'm going to express those complex, boy, that's not very accurate, but it's supposed to be symmetric up and down. But I'm going to represent those complex poles as one term, let's say a cosine piece. Or somebody might say, I'm going to represent them as a sine and a cosine piece, and that would be equally valid. But if we now say, okay, the structure is going to be, let's say, a e to the minus 3t cosine 4t plus theta plus a b e to the what? And I would have to give you more information before you could actually find the a and the b. If somebody said, oh, it really needs to have 3 terms, well, it sort of has 3 terms implicitly because that angle is there. But if somebody wants to write it another way, they could say, oh, it's a1 e to the minus 3t cosine of 4t plus an a sub 2 e to the minus 3t sine of 4t plus a b e to the minus 5t, t greater than or equal to 0. And that would also be correct. Is this system, just given the pole zero diagram, is this system stable? Yes, because all the poles are in the left half plane. Here's something that, have we talked about this? I haven't really emphasized this, but when we start talking about Bode plots, we will need to make sure that our system is minimum phase. Do you remember what I defined minimum phase to be? A system is minimum phase if all of its poles and zeros are in the left half plane. That was the definition that, I don't know, I quickly probably discussed or mentioned earlier sometime. I thought I did. Maybe it was somewhere else. But is this system then, does this system satisfy that definition? Yes, and so now this is what we would be worried about sketching in terms of the Bode plot. So this system indeed is minimum phase. Now if somebody said, well, what if I excite this system with an x of t equal to, oh, let's say square root of 2 cosine of 3t. And somebody says, what's the sinusoidal steady state output? Now what I want you to be able to do is actually show me or compute or be able to find what's going on to make up that sinusoidal steady state output. What are you interested in now? So now what can you tell me if somebody gives you x of t that looks like that? What's important in that piece of information of the input? The frequency, how fast you're shaking the system. This is critical, this little piece. And that's now 3 radians per second, which the homework now may be talking about hertz, etc. But if your omega is 3, then the frequency associated with that is 2 pi f. And so f in this case is roughly 1/2, 3 divided by 6 in very round terms. But your frequency is now 1/2 a hertz. And that's how fast you're shaking the system, roughly in round terms. And if somebody wanted to know the period of that waveform, that would just be 1 over f. But that's a critical piece of information which now says, oh, now I need to find what's happening right here at J3. Meaning, how do all of these pieces combine? I need to worry about this length. I need to worry about this length. I need to worry about this length and that length. Ooh, that was supposed to be a straight line. And I need to know these angles. I add the angles of the zeros and I subtract the angles of the poles because the zeros are upstairs, the angles are downstairs. And all of that you can then combine together to determine how the sinusoidal steady state output is going to behave. And somebody would actually have to give you the DC gain before you could really find the magnitude of that transfer function. Question? Yes, so now what you could do is the question I think was, couldn't you just do the following? Couldn't you just say, oh, I have a pole, or where was my 0? I had a 0 here, so I know I have that factor. I had a pole there, and I had another collection of poles at, is this where I had them? What I didn't know was this unknown gamma. And if somebody gives me the DC gain, I can compute that gamma. What's my DC gain for this system? It's when h of s is equal to 0. And in this case, then, we would have gamma 2 over 5. And here we would have, whoops, you guys need to wake me up. That should have been a square, right? That was the s plus 3 squared. And so in this piece, we have 3 squared plus 4 squared. And if somebody said, oh, the DC gain of that system was 5, then you would solve for gamma to see what that gain was. So that gamma now is going to be, maybe I should have done something else. You have this 5 times that 5 times, there I have 9 plus 16, or 25, all divided by 2. So I have 25 squared, which is 625 divided by 2. That's now my number gamma, if I had a DC gain of 5. Question? And then what you could do is you could say, oh, I need h of J3, and now you plug in everywhere you see an S, you replace it with J3, and you could numerically compute that complex number associated with the transfer function at the frequency 3 radians per second. Yes, and so now you would have 312.5, and this would be J3 plus 2 all over J3 plus 5, and then you have J3 plus 3 squared plus 4 squared. And that will give you a complex number, and now you take the magnitude of that and the angle of that to obtain the information you need Is that making sense? And that's now your sinusoidal steady state. Question? No, the question was, I thought you had to multiply by 2. That 2 was if we had it in terms of K1 and K1 star. That's where that 2 came from. So don't confuse that. That's correct. We did have a 2 in that expression at some point, but after we take all of that into account, all we really are doing is scaling the original x amplitude by the gain of our system's magnitude response at the given frequency of excitation. Is that making sense, or is that okay? What else? Oh, let's talk about convolution. So your third major topic is the topic of convolution. And I still haven't seen a lot of traffic on those videos. but maybe you all know how to do this. But if I gave you an input waveform X and an impulse response H, you should be able to tell me when the output response is going to begin and when it's going to end. Does that make any sense? If your system had an impulse response that looked like this, and now you start exciting it, with X, and if I gave you nothing more than that, I could quickly find out some information if you sort of know the crude aspect of convolution by saying, okay, if this system was excited by an impulse waveform, if I hit it with an impulse, then its natural response is going to be what h of t demonstrates. It's going to then just decay down to 2 as a straight line. That's not a linear circuit that we've created, but that's just what I'm sketching to make my discussion easier. Now we hit it, in this case, with a signal X that begins at 4. When is Y going to begin? If t was in seconds. When is Y going to end? Does everybody see that? And that should be easy enough to believe if you're starting to do some convolution problems. I might ask you something that you haven't had to do yet, or maybe you have. What if I ask you to evaluate the output response, y of t, at a particular or at a specific time? What if I said, what's y of t at t equal 3? That's 0, right? It hasn't started to happen yet. So y of 3 is 0. If I said, oh, that was too easy, so let me make it a little bit at t equal 5. Now will you have a non-zero value for an output? Do you expect something of y of t? If you were flipping and sliding x of t, x of minus lambda now looks something like this. X of t minus lambda looks like that. And now we're going to slide that through this h of t. Or now I'm going to make this in fact, what I want to do is I want to replace this t with 5. Is that what I said, y of 5? And that now says that this rightmost endpoint of x of t minus lambda is now going to be right at lambda equal 1. And I now need to find the area underneath that product and integrate that particular expression. Meaning y of 5 would be the integral of whatever this was. Let's say it's minus gamma lambda. Is that okay? So this is minus gamma lambda. And I don't know, let's say this was 5 d lambda. And what are my limits of integration? Oh, maybe that was a poor choice of 5. I've got too many 5s. So let me say this was 3. What are my limits of integration? So it's 0 to t minus 4. And I actually wanted you to do, so this was y of t, but I actually said, oh, replace that with 5, so now I can plug in a specific value of 5, and I integrate from 0 to 1. Is that making any sense? So if I ask you for a specific value of the output, that's what I'm looking for, is that you know that you need to slide it through to the right point, but now really I'm just looking for one number. If I didn't say that, if you were trying to do the convolution problem, now you would have different overlap patterns. Question? So let me see if I understand your question. You're saying, what if the impulse response was that way or not? Which way? Like this? So if this is t minus 4, is that what you're asking? And this is still, I don't know, t minus 7. Okay, so I've expanded things, the picture. It really doesn't matter how they overlap. What you are interested in is the functional form of these waveforms. Meaning, let's say that this is now flatter for whatever reason. So let's say this is minus beta lambda. So it's beta instead of gamma. But I still have that slope, and this is still, let's say, 3. What I'm interested in is not so much how these pictures overlap, it's their interval of support, their overlap, and the functional form of these. This guy is simply 3, and this one is minus beta lambda. I now say, oh, and let's just say that this endpoint over here was, well, I know that distance is 3, so let me say this was going out to 5. Is 5 a bad? Why do I keep picking 5? Must be on the exam, and I haven't created the exam. So let's say 8. Is that okay? Now if I wanted, when is this picture valid? So this is this interval and limits scenario, and they're not necessarily the same. So the interval where this picture, I can't spell. Maybe I did spell right. I just can't see. So now when is this interval valid? And it could be that maybe you didn't know that the one was 3 wide and the other one's 8 wide, and you go, well, I also know that this needs to be less than 8. What you do is you look at all of those and you find the most restrictive or the intersecting ones of these. Meaning this one gives you t is less than 12. This one gives you t is greater than 4, and this one gives you t is less than 7. And so now you say, oh, the intersection of those is t is bigger than 4 and less than 7. And that's the interval when this is true. So this picture is true for t between 4 and 7. And now what do the limits look like? This is now y of t is equal to, it's minus beta lambda. That was the functional form of your h of lambda. Your x was constant, that was 3 d lambda. And now what are your limits of integration? Is that 4 to 7? Oh, we're going from 4 to 7 today. Is that okay? I'm sorry, no, just joking. I would be in trouble if we went to 7. I'm always in trouble, so it doesn't matter. But what are my limits of integration? They will be the lower limit, and now it's where the blue and the red crosshatching is true or exists. And that's true from 0 right here up to this point, which is t minus 4. Meaning my limits are now from 0 to t minus 4, and this result is valid as long as t stays between 4 and 7. And 4 and 7 are not the same as 0 to t minus 4 necessarily. So your intervals and limits can be different, and that's one of the big points I want to make sure you're clear on. Questions on that? Yes?
How do we know when y can't y and get back to the other problem? Again, set t equals 9.
Where are we at? I'm sorry. Right. Keep going up. So your question is, how do we know that t is equal to 9?
Yeah, that ends at 9.
That it ends at 9. So the way that it ends at 9 is, you know that whenever you hit this system, if you hit it, it's going to last for that duration, 2 seconds. So now this particular input that we have illustrated, we said it's going to keep exciting the system until 7 seconds. So now we stop exciting the system at 7. Well, we know that the transient is going to last 2 seconds beyond when we excite it, because this picture for H shows us what happens when we hit it with an impulse. And an impulse is instant, and it happens at t equals 0. And that h of t says, oh, it lasts only for 2 seconds beyond when we hit it. The x that we are hitting it with in this example is this guy that starts at 4. So we start as soon as we get excited. So it starts at 4, but then we quit hitting it at 7. And if we stopped at 7 and we wait 2 more units of time, that's when we will no longer see the output. So we have to wait the length of our h of t beyond when we excite it. We excited it until 7. Well, it's going to keep shaking until 2 seconds later. And that's where the 9 comes from. Does that help? Is everybody clear on 4 and 9? And that's where, so this actually, you may think this is trivial, but this is a good way to check your work. Now when you're doing your convolution, if I said do the convolution with this h and this x, and you end up with non-zero expressions for y outside of 4 and 9, you know something's wrong. So if you said, oh, y of t functionally is something out to 20, whoa, something's not right. I did something wrong, because I should only expect an output between 4 and 9. Is that making sense? Now, if if indeed we did hit this system H with this X, is the output Y going to look like X, shape-wise? If I hit if I hit the system that has an impulse response that looks like H of t with this waveform X of t, is my Y of t going to look like X of t? And if it's not, why not? Or what do we want to have happen or true in order for Y to look more like X? What do we need to have happen? We want H to look more and more like an impulse response. The more H looks like a true impulse response, the more Y is going to look like X. Is that making any sense? Does that mean anything to you? I mean, the more it looks like delta of t, so if you had h of t, let's say this is h1, and h1 looks like this. And now h2 is a different system, and it looks like this. Which of h1 and h2 look more like an impulse? H2, right? That looks more like an impulse waveform. It really accents what's happening right at 0, and it falls off rather rapidly. The ideal is to have our system have an impulse response that is the impulse response, and then whatever you put in, you're going to see exactly what you put in. If you said, okay, here's another way of looking at this. What is h sub 1 of s versus h sub 2 of s? So suppose that I said this was 5e to the minus 5t, and this was 20e to the minus 20t. Can you now find capital H1 and capital H2? This is now 5 over s plus 5, and this is 20 over s plus 20. What are the DC gains of those? 1 and 1. And what do they look like in terms of frequency response? If I now said, what does H1 of j omega look like? The magnitude of 5 in the numerator is 5, and the magnitude of j omega plus 5, the way we are going to work with that is we're going to say, oh, we'll just approximate that to be flat out until omega equals 5, and then it will start falling off at 20 dB per decade. This would be H1's magnitude response. What's H2's look like? It was exactly the same at DC, wasn't it? It was 0. But now H2 we are going to worry about it being flat out to 20, and then it will go down. So now which one is in terms of a low-pass filter, which one has a narrower bandwidth? H1. It's not passing as many frequencies, so it's slower. It's responding much slower, and that's why if you put a signal through H1, it will distort it more than putting the signal through H2, because H2 is passing higher frequencies. That's what we're moving towards in combining all of this. You have a lot of tools now at your disposal. You have the ability to find transfer functions. You have the ability to solve circuit problems, the complete solution, and incorporating all initial conditions and transients. You know how to convolve signals. If you don't know how to find a capital X of S, you can work with the X of t and find the impulse response and convolve those to find the Y of t numerically or with the convolution integral. If you know how to find capital X of S, you can multiply capital X of S with H of S to find Y of S and inverse Laplace transform Y of S to obtain Y of t. Which is so now the question was, am I going to worry at this point with the dual concept of convolution in the frequency domain? That corresponds to product in the time domain. Let's not worry about that. Let's just learn the one direction to begin with. Let's get comfortable with that, and then we'll move forward. Once you feel warm and fuzzy with that, then we can move back and forth with these different ideas, and that's really the next class. That's more like what you might see in 340. Yes? So the question was, you're trying to push your poles out to negative infinity. It really depends on what you're wanting to accomplish. If, for example, you may not want a sharp square pulse to be going through your system. You may want to smooth that, or you may have a digital system that can only sort of create ones and zeros. So you have these really sharp waveforms that are pulses. Maybe somebody says, oh, I can turn this off and on, and I can create a waveform like that. And you go, well, I don't want that. I actually want more sinusoidal type bumps. Then what do? Well, you filter out the high frequency content in these waveforms. And what's high frequency? It's these sharp corners. So if you filter this out and maybe only retain the fundamental frequency in that very harmonically rich waveform, now what you want are these red pulses. And that's maybe what you want. And that tells you where you need to put your low-pass filter cutoff frequency. So it really depends on what you're getting or wanting to accomplish. If you want your output, the red, to look like the green, then yes, you want your filter to have a high bandwidth, to have your pole way out there in the left half plane, which is what H sub 2 is doing better than capital H sub 1. If you had to sketch the pole zero diagram of those two transfer functions. So that's where I want you on Thursday, is to be able to play with all of these ideas. Now you can start to see how they all, I hope, fit together. Other questions before I shut it down? You'll get 3 sheets of notes. Yes. If you need them. You may not need that many notes. So only produce what will be efficient for you during the exam. And you might ask that question tomorrow so that everyone in class understands what's allowed. I'll see you tomorrow.